Hello everyone, this is Binghan He from the Human-Centered Robotics Lab at the University of Texas at Austin. Today, I want to introduce to you a new method of safety verification using the estimated states of an uncertain dynamical system. Let me first talk about why we need a new safety verification method for the uncertain systems. Usually, safety verification is done by calculating the value of a barrier certificate. This barrier certificate is greater than 0 in the unsafe state space region and less than 0 in a safe state space region. Similar to a Lyapunov function, the barrier certificate decreases in the state space over time. If you can find a barrier certificate for a system, then the system is verified to be safe. The barrier certificate only focuses on safety verification, while the control barrier functions include feedback controllers which guarantee the closed loop satisfy the barrier certificates. The barrier certificates and the control barrier function require to know the state of the system for safety verification and safety guarantee purposes. However, some of these states are not directly available for some dynamical systems. For example, let's take a look at this one-off human-robot interaction model, where the human is modeled as a mass, a spring, and a damper. We have the direct measurement of the input, which is the robot force, and we'll also have the direct measurement of the output, which is the human-robot contact force. Even though we can put a sensor to measure the robot position, however, the spring origin of the virtual human spring is unknown. Therefore, the deflection of this virtual human spring is not directly available. We can use state estimators such as Lyapunov observer, which estimate the true states of a certain linear system asymptotically. For non-linear system or an uncertain linear system, we can still use an extended Lyapunov observer. Instead of converging to the true state, the estimated states converge to a residual set around the true states of an uncertain dynamical system. But however, the system can still go unstable and violate the safety constraint before the state estimation becomes valid. Therefore, in this research, we consider a transfer function of a system with bounded uncertain parameters. There are many types of state space realization of a transfer function, but for the convenience of expression, we'll use the observable canonical form for the state space equation. If we have the safety controller design in advance, we want to find a robust estimator which verifies the safety of the system at all time with only using the input and the output measurements. First, since we use the observable canonical form of state space realization, we can easily turn our state equation into a form which is very similar to a Lyapunov observer. The A0 matrix of this equation still follows the rule of the observable canonical form, but its characteristic equation is completely user-defined. The By and Bu matrices contain all the uncertain parameters of the uncertain system. But this Lyapunov observer is not realizable because the unknown parameters in By and Bu. To solve this problem, we can turn this Lyapunov observer into an identifier-based estimator, which is just a pair of sensitivity filters of the input and the output signals. Notice that these two sensitivity filters are automatically in the controllable canonical form, since there is no uncertain parameters of these two dynamic equations of the identifier-based estimator. The estimated states of this identifier-based estimator is totally available. We can also prove that the estimated state of this Lyapunov observer is dependent on the state of the sensitivity filters and the uncertain parameters. To be more precise, It is linear with the uncertain parameter matrices By and Bu. Before I move to the proposed method, I want to recall a lemma of a vector norm function. There are three properties, property A, B, C, for vector norm. This means if a vector function satisfies all these three properties, it is a vector norm function. But if we can only prove the satisfaction of this property A and property B, then the triangle inequality property holds if we can also prove this vector function has its unit ball as a convex shape. So the reason we care about this lemma is because we want to use it for creating us vector norms based on Lyapunov functions. Let us first consider a quadratic Lyapunov function. The square root of a quadratic Lyapunov function can be proved to be a vector norm function because it satisfies the first two properties of the vector norms, and its unit ball is a convex shape. Let us call this new vector norm function a Q-norm. We can use the triangle inequality to break the Q-norm of the true state into a Q-norm of the estimated state and a Q-norm of the estimation error. Since the state estimate is linear with the matrices of the uncertain parameters, we can find the upper bound of this term very easily. And on the other hand, we have the estimation error converged from its initial value to 0 exponentially. But the ellipsoidal invariant set of the quadratic Lyapunov function is still not the ideal way for representing the entire safe state space region. If we want to enlarge the invariant set, we can consider a composite quadratic Lyapunov function. Its positive definite matrix Q is in a convex hall of multiple different Q matrices of different quadratic Lyapunov functions. The square root of this composite quadratic Lyapunov function can be proved to be a vector norm function because its unit ball is the convex hall of all the ellipsoidal unit balls of all different quadratic Lyapunov functions. So let us call this new vector norm function a C-norm. Similarly, this C-norm can also be bounded by the C-norm of the estimated state and the C-norm of the estimation error. We use these two vector norm functions to build barrier pairs. And a barrier pair is a pair of a barrier certificate and a stabilizing controller. While we are using this stabilizing controller, the sublevel set of this barrier certificate becomes an invariant set. While we are inside this invariant set, the state and input constraints are both satisfied. Let us consider the quadratic Lyapunov function for the system with a static output feedback controller. The unit level set of this quadratic Lyapunov function is inside the safe state space region. Then we obtain a barrier pair of a barrier function based on the Q-norm of this quadratic Lyapunov function and this output feedback controller. Similarly, we can build a barrier pair based on the C-norm and the output feedback controller. Now, the question is how we can synthesize these barrier pairs based on the output feedback controllers. First, we have a closed loop state space equation of the system. The closed loop A matrix of the system is in the convex hall because of its uncertain parameter defined in the transfer function previously. We can also represent the state and input constraints as the polytopic regions. These constraints can be turned into linear matrix inequalities for shaping the quadratic Lyapunov functions. For the composite quadratic Lyapunov functions, we want to have an additional LMI to constrain its direction for each ellipsoid. So we can let the unit level set of each of these quadratic Lyapunov functions expand in different directions such that the overall region of attraction for the composite quadratic Lyapunov function is improved. We can also encode a minimum decay rate in the LMI for the Lyapunov function stability. It is easy to find an A0 matrix for the identifier-based estimator. But through an additional convex optimization, we may be able to find an A0 matrix with an even higher decay rate than the guaranteed decay rate alpha 0. After obtaining the barrier pair and the identifier-based estimator, we are able to calculate the upper bound of the barrier function. This estimated barrier function has a term of the C-norm of the estimated state. We do not know the initial estimation error, but if we assume that the state starts from somewhere inside the invariant set of the C-norm, then the initial value of the C-norm of the estimation error is bounded by 1. If we have an arbitrary input U hat, which caused the upper bound of the estimated barrier function higher than the threshold B bar, we will switch to the safety backup controller KY. If the upper bound of the estimated barrier function is lower than a lower threshold B underbar, we can switch back to the input U hat. Let us now consider an example of a simplified human exoskeleton interaction problem. The human is modeled as a virtual spring with the unknown spring origin. The exoskeleton is modeled as a mass with a linear damper. The exoskeleton actuator provides us an input force U, while the human responds with a human contact force Y as the output. If U equals to a static output feedback controller KY, then this exoskeleton becomes a force amplification exoskeleton. The closed loop A matrix is in a convex hull because it's uncertainty in the human stiffness. In order to reduce the load applied on the human, we want to constrain the human contact force and the changing rate of the human contact force. This will give us some state and input constraints. We simulate the system by releasing the state from the boundary of the invariant set. Certainly, the system should be stable with this static output feedback controller. But our purpose is to make sure that the estimated bound of the barrier function is greater than or equal to the true barrier function value. Then we simulate the exoskeleton to check a sinusoidal signal, which is designed to violate the contact force constraints. We want to see if the safety backup controller can be triggered before the safety violation. So in this figure, we can see the state stops moving further when it is close to the boundary of the unit bore of the C-norm. And in this figure, we can see the true barrier function value is always lower than the upper bound from the estimated barrier function. And that's all for my presentation. Thank you for your listening.